In this episode, we take on a security challenge that is both technical and deeply human, because it involves systems that can affect physical safety in the real world. Industrial control systems, ICS, and supervisory control and data acquisition, SCADA. Environments help run utilities, manufacturing lines, building systems, water treatment, pipelines, and many other operations where reliability is not just convenient, but essential. New learners sometimes assume that security is always about locking things down as tightly as possible. Yet in safety-focused environments, the first responsibility is often to keep the process stable and predictable. That does not mean security is optional, but it does mean security decisions must respect the reality that an unexpected change, a sudden reboot, or a blocked message can create dangerous conditions. The aim here is to understand how security architecture can reduce cyber risk while still protecting the safety and continuity goals that these environments exist to serve. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A clear starting point is understanding what makes ICS and SCADA different from typical office or web environments, because those differences shape both threats and defenses. Many control systems were originally designed to be isolated, long-lived, and stable, with the assumption that only trusted operators would interact with them. They often use specialized devices, specialized protocols, and a mix of digital and physical feedback loops that keep a process running. They also tend to have long replacement cycles, which means older components may remain in use long after modern security expectations have changed. Another major difference is that availability and deterministic behavior can be more important than confidentiality in the moment, because a delayed control message can matter more than a leaked report. Beginners also need to realize that safety systems and control systems may be interconnected, sometimes directly and sometimes indirectly through shared infrastructure. So security failures can have consequences beyond data loss. When you recognize these distinctions, you stop trying to force office-style security onto a control environment and start designing controls that fit the mission. To secure these environments without breaking safety operations, you need a high-level mental model of how control systems are structured and how control happens over time. Many control environments have layers, including field devices that interact with the physical world, controllers that execute control logic, and supervisory systems that monitor and coordinate. A common device class is the Programmable Logic Controller, PLC, which reads sensor inputs, applies control logic, and drives actuators like valves, motors, and pumps. SCADA systems often sit above that level, collecting measurements, displaying status to operators, and enabling higher-level control actions. There may also be engineering workstations used for programming and maintenance, historians that store process data, and gateways that connect control networks to business networks. Even if you do not memorize every component name, the important idea is that a control environment is a system of systems where each layer depends on the reliability and integrity of the others. Security architecture must therefore focus on controlling who can reach which layer, which actions are allowed, and how changes are made safely. Risk in ICS and SCADA starts with understanding what must be protected, and for safety operations, the primary asset is often correct and stable process behavior. Confidential data exists, such as recipes, operational schedules, and configuration details, but the most immediate risk may be manipulation of control signals or sensor readings that alters the physical process. Integrity becomes a central security property because false readings can cause operators to make dangerous decisions, and malicious commands can cause equipment damage. Availability is also crucial because loss of visibility or loss of control can force emergency shutdowns or lead to uncontrolled conditions. Another risk is loss of trust, because if operators cannot trust their displays and alarms, they may fall back to manual procedures under stress, which can introduce new hazards. A beginner misconception is to treat all cyber risk as data theft, but in control systems, the bigger concern is often unsafe change, unsafe operation, or prolonged outage. Security architecture, therefore, begins by mapping out which functions are safety critical, which are mission critical, and which are merely convenient, so that controls can be tailored to protect the most important outcomes. Threats in control environments often begin at the edges, where connectivity or human workflows create entry points that were not originally designed for adversarial activity. Remote access for maintenance, vendor support, and monitoring is a common need, and if it is implemented loosely, it can become a direct path into sensitive control networks. Portable media used for updates or data transfer can introduce malware into otherwise isolated environments. Engineering workstations can become high-value targets because they may hold the ability to change control logic, upload configurations, or modify safety thresholds. Business network connectivity can also introduce risk, especially when reporting, analytics, or centralized monitoring leads to bridges between office systems and control systems. Another entry path is credential reuse, where shared passwords or default accounts allow attackers to gain access without sophisticated exploits. Beginners sometimes assume attackers must hack devices directly, but in many cases attackers walk in through weak access pathways that exist for legitimate reasons. The architectural goal is to preserve the legitimate workflow while making the pathway controlled, monitored, and resistant to abuse. Segmentation is one of the most effective architectural tools in ICS and SCADA security because it creates clear boundaries that reduce the blast radius of compromise. A strong design avoids a flat network where every device can reach every other device, because that structure makes lateral movement easy and makes containment difficult. Instead, you design zones based on function and criticality, separating business systems from control systems, separating supervisory systems from field networks, and separating engineering functions from routine operations. The boundaries between zones should be enforced through explicit policy, meaning only the necessary flows are allowed, and everything else is blocked. It is especially important to isolate management interfaces and programming pathways, because those are the places where changes can be made quickly and at high impact. A beginner misunderstanding is to think segmentation is only about performance or organization. But here segmentation is a safety-preserving measure because it prevents a compromise in a less critical area from instantly becoming a compromise in the control core. When segmentation is well designed, it supports both security and operational stability by making communication paths predictable and purposeful. Designing access control in control environments requires extra care because operators need reliable access during normal operations and during emergencies, but unrestricted access can make the environment easy to misuse. A common challenge is balancing usability with least privilege, meaning people should be able to perform their job functions without having permissions that allow unnecessary and risky actions. Operator accounts should typically be able to monitor and control within defined bounds, while engineering accounts should be more restricted and used only for approved change activities. Administrative access to critical devices should be tightly controlled, and shared accounts should be avoided because they destroy accountability and make revocation difficult. Identity and authorization decisions must also consider service accounts and machine identities, because many control environments rely on automated data collection and control pathways that use non-human access. A safe architecture often includes separate pathways and separate roles for routine operations versus maintenance and change, so that the everyday control surface is smaller and more stable. Beginners sometimes expect one universal login, but in safety operations, the separation of roles is part of safe design, not an inconvenience. Change management is where security and safety meet most directly, because changes to control logic, firmware, network paths, or alarm thresholds can have immediate physical consequences. A good architecture treats change as a controlled process, not an ad hoc activity performed whenever someone has time. That means defining how changes are requested, reviewed, tested, scheduled, and validated. And it also means deciding what changes are allowed during active operations versus maintenance windows. The goal is to avoid situations where security improvements are implemented in a way that disrupts control behavior, such as patching a device at the wrong time or introducing a new network rule that blocks essential traffic. It also means having rollback plans, because even well-intended changes can have unexpected effects in complex systems. A common beginner misconception is that patching is always the top priority, but in ICS environments, patching must be balanced against operational risk and safety risk. The architectural answer is not to avoid patching forever, but to build a lifecycle plan that includes testing, stage deployment, and compensating controls when patching is delayed. Monitoring and detection in control environments must be designed to support fast understanding without overwhelming operators or creating false alarms that get ignored. Visibility is critical because many attacks involve subtle changes, unusual commands, or slow manipulation rather than obvious disruption. A strong design includes logs and telemetry from key systems, such as control servers, engineering stations, gateways, and critical controllers, and it ensures those logs are protected from tampering. It also includes network monitoring that can detect unusual communication patterns, such as a device suddenly talking to an unexpected peer or a large volume of traffic in a normally quiet segment. However, monitoring must be deployed thoughtfully because excessive scanning or intrusive inspection can disrupt sensitive devices or introduce latency in real-time pathways. Beginners sometimes assume more monitoring is always better, but in safety environments, the monitoring solution must be compatible with the process and must not become a source of instability. A well-designed monitoring approach focuses on meaningful signals and supports quick triage so teams can distinguish equipment issues from cyber issues. That ability to distinguish is itself a safety feature because it reduces confusion during incidents. Remote access is one of the most important topics in ICS security because it is both necessary and risky, and the safest approach is to make remote access explicit, limited, and strongly authenticated. Vendors and maintenance teams often need access for diagnostics and support, but direct remote connectivity into sensitive zones creates a powerful attack path. Architects usually design remote access so it terminates in a controlled boundary zone and then allows only the specific actions and destinations needed, rather than granting broad network presence. Remote access should also be tied to individual identities rather than shared credentials, because accountability and revocation are crucial when access spans organizational boundaries. Another risk is that remote access can become permanent even when it was originally intended for temporary use, so governance and periodic review are part of the architecture. For beginners, it helps to understand that secure remote access is not defined by being encrypted, but by being constrained in scope and monitored in behavior. When remote access is designed as a controlled workflow rather than a wide open tunnel, it supports operations while reducing the chance of a remote compromise turning into a process safety incident. Protecting engineering workstations and programming pathways deserves special attention because they often have the ability to change logic and behavior at the controller level. If an attacker gains access to an engineering workstation, they may be able to modify PLC logic, adjust set points, or change how alarms behave, which can cause harm even if the rest of the network is segmented. A secure architecture treats engineering tools as privileged assets, placing them in restricted zones, limiting their network reach, and controlling when and how they are used. It also includes strict control over project files, configuration backups, and software used to program devices, because these artifacts can be manipulated to introduce malicious changes that look legitimate. Another important concept is ensuring that changes are traceable, meaning you can determine who made a change, what was changed, and when it occurred, because investigations and safety reviews depend on that clarity. Beginners sometimes focus on external attackers, but insider mistakes and careless workflows can produce similar outcomes, so controls should protect against both. When engineering pathways are secured, the environment becomes much harder to alter silently. Data integrity in control systems is not only about protecting stored files, but also about protecting the meaning of sensor readings and control commands as they move through the system. If an attacker can spoof a sensor reading, the system may react incorrectly, and if an attacker can replay or inject commands, equipment may respond in dangerous ways. Architects therefore care deeply about trust in communications, including which devices are allowed to send commands, which devices are allowed to report measurements, and how systems detect anomalies. Even when control protocols have limitations, architecture can reduce risk by limiting where those protocols can travel, limiting which devices can speak them, and monitoring for unexpected messages. Another integrity concern is time synchronization, because accurate time supports event correlation and can affect the validity of certain security mechanisms, and time problems can create confusion during incidents. Beginners sometimes treat integrity as a cryptography topic, but in control systems, integrity is often about ensuring the right device is making the right statement at the right time within expected ranges. When integrity is protected, operators can trust what they see and react appropriately, which supports safety. Resilience and recovery planning are crucial because control environments must be able to return to safe operation quickly, even after cyber events or equipment failures. Recovery is not just about restoring data. It is about restoring correct control behavior, correct configurations, and operator visibility. A good architecture includes reliable backups of configurations, logic, and critical system states, stored in ways that are protected from tampering and accessible during an incident. It also includes clear processes for validating restored configurations, because restoring a compromised or outdated configuration can reintroduce risk. Another key idea is maintaining the ability to operate safely in degraded modes, meaning if a supervisory system is unavailable, operators still have a safe way to monitor and control critical functions. Beginners often imagine recovery as a simple restore, but in safety operations, recovery must include careful verification, because the wrong restore can be more dangerous than no restore. Resilience planning also includes redundancy where appropriate, but redundancy must be designed carefully to avoid creating hidden pathways or shared failure points. When recovery is planned as part of architecture, incidents become more manageable and less likely to spiral into unsafe conditions. Physical security plays a larger role in many ICS environments than beginners expect, because field devices, cabinets, and control rooms can be physically accessible in ways that office systems are not. If an attacker can access a controller cabinet or a network port in an operational area, they may be able to connect unauthorized devices, capture traffic, or alter equipment directly. Even well-designed network segmentation can be undermined if unauthorized physical connections can be made inside a trusted zone. Architects, therefore, include physical controls such as controlled access to critical areas, tamper-evident measures for cabinets, and procedures for escorting visitors and contractors. Physical security also supports safety because it reduces accidental interference with equipment and reduces the chance that well-meaning staff introduce insecure devices for convenience. Another physical concern is environmental stability, such as power and temperature, because unstable environments can cause failures that look like cyber incidents and create confusion during response. Beginners sometimes treat physical security as a separate field, but in control environments, physical and cyber are deeply intertwined. A durable design treats physical access pathways as part of the overall threat model and closes them where feasible. A central theme in securing ICS and SCADA without breaking safety operations is that security controls must be validated against operational reality, not only against theoretical best practices. Some controls that are common in office environments, like aggressive scanning or frequent forced updates, can disrupt control devices or cause unexpected behavior. That does not mean you accept risk. It means you choose controls that align with the stability needs of the process and you test changes carefully before deploying them broadly. Architects often use compensating controls when direct controls are risky, such as stronger segmentation when patching is slow, or tighter remote access constraints when endpoint controls are limited. Another important practice is involving operations and safety stakeholders in security decision-making, because they understand the failure modes and the timing constraints of the process. Beginners may assume security is a separate team's responsibility, but in safety environments, security is a shared architectural concern because security failures can become safety failures. The best designs are not the strictest on paper, but the most reliable in practice, because reliability keeps protections in place rather than being bypassed under pressure. Incident response in control environments needs a different mindset because the first objective is often to maintain or restore safe operation, not simply to isolate everything instantly. In an office breach, you might isolate systems quickly even if productivity suffers, but in a control environment, Abrupt isolation can create dangerous conditions if it removes visibility or interrupts control pathways. A good architecture supports response by ensuring there are safe containment options, such as isolating a compromised segment while maintaining essential control functions. It also supports response by providing clear monitoring data and clear system diagrams, so responders understand what can be disconnected safely and what must remain connected. Another architectural feature is having predefined communication and escalation paths between cybersecurity teams and operations teams, because misunderstandings during incidents can cause delays or unsafe actions. Beginners may think incident response is mostly a technical procedure, but in safety operations, it is also a coordination challenge where timing and clarity matter. If the architecture supports careful containment and clear situational awareness, response becomes more controlled and less disruptive. That reduces the chance that security actions themselves become part of the hazard. As we bring everything together, the main idea is that securing industrial control systems, ICS, and supervisory control and data acquisition, SCADA, is an exercise in protecting trust, integrity, and resilience while honoring the safety mission of the environment. You reduce risk by designing segmentation that creates clear boundaries and prevents casual lateral movement, while ensuring required communications remain reliable. You protect access pathways by separating operational roles from engineering roles, controlling remote access carefully, and treating programming tools and administrative interfaces as privileged assets. You preserve integrity by limiting who can send control commands and who can influence sensor data, while monitoring for unusual behavior in ways that do not destabilize the process. You maintain resilience with secure backups, verified recovery methods, and safe degraded operation options that keep safety outcomes front and center. Most importantly, you avoid fragile designs by choosing controls that can be operated consistently, tested safely, and maintained over time, because safety operations cannot tolerate security that works only in ideal conditions. When your security architecture respects the responsibility to keep people and physical processes safe, you get an environment that is both more defensible and more reliable, which is the outcome this topic is ultimately aiming for.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.